Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Semiconductor Materials and PN junction diode from the paper Semiconductor Materials and Devices. So students, let us see what we are going to learn about this module. First, semiconductor growth techniques, that is for the growth of crystals and thin films, will be discussed. Second, the different growth techniques of PN junction fabrication. Third, we will be discussing about the forward and reverse biasing of PN junction diode. So let us start with a basic introduction about the module. A semiconductor is generally defined as a material with electrical conductivity or resistivity lying between that of a metal and an insulator. The best known semiconductor is silicon and germanium. And the silicon is having a band gap of 1.1 electron volt. Elemental semiconductors are there such as silicon and germanium, which consist of single type of atoms and have similar tetrahedrally bonded crystal structures. So, compound semiconductors, they are formed from the elements of group 3rd and 5th or 2nd and 6th of periodic table. Pure semiconductors, they are usually single crystals of pure silicon or germanium. They are insulators at very low temperature. So upon increasing the temperature, some of the electrons, they gain thermal energy and are free to move and conduct electricity. These electrons leave behind the vacancies or holes which carry a positive charge equal in magnitude to that of an electron. These holes can also act as current carriers. So a semiconductor consists of two types of charge carriers, electrons and holes. Semiconductors, they can be doped with pentavalent or trivalent elements in order to increase the concentration of electrons and holes. These elements can act as donors or acceptors. Silicon, being a tetravalent atom, contains 4 electrons in its outermost shell. So a pentavalent such as phosphorus, arsenic, antimony, they will replace a silicon atom and donate 1 extra electron. A trivalent atom such as aluminium, boron, gallium, it will act as an electron acceptor, giving rise an extra hole. Semiconductors having electrons as the majority charge carriers, they are known as N-type semiconductors, while those having holes as the majority carriers are P-type semiconductors. Now a PN junction diode, it is a fundamental unit of all electronic circuits and devices. It is a 2-element device with both P-type and N-type semiconductors. The term diode was originally coined to refer to vacuum tubes that had 2 electrodes, an anode and a cathode. There could be contrasted with the triodes, tetrodes, pentrodes, etc., which were vacuum tubes with 3, 4 or 5 electrodes. Originally, diodes were simply rectifiers. Electrons would flow in a vacuum diode from a heated cathode through the vacuum to the anode, where the anode was made positive with respect to the cathode, but when the applied voltage was reversed, no current would flow because the anode was not a source of electrons. So the device would conduct electricity only when the diode was made more positive electrode. Later, when semiconductor devices were produced that exhibited similar electrifying properties, they are called as diodes too. Though the term diode, the anode and the cathode, they are less often used. Semiconductor growth techniques. So students, first let us discuss the crystal growth techniques. Semiconductors can be in the bulk as well as in thin film form. So the basic techniques for the growth of semiconductor single crystals will be the following. So first we will discuss the Czochralski method. This method utilizes a seed crystal of the material to be grown. So a crucible containing the raw material in polycrystalline form is heated so as to melt the material. So the seed crystal is lowered into the crucible and withdrawn with continuous rotation. The material solidifies into the same orientation as that of the seed crystal. So this technique uses an apparatus called as crystal puller, whose schematic is shown in this figure. And it is to be noted that the puller has three main components. First, a furnace with a power supply which includes a crucible made of fused silicon or SiO2, arrangement for rotation, that is clockwise, a graphite suspector, a rotation mechanism for clockwise, and a heating element. Second, an arrangement for pulling crystal including a seed holder and rotation mechanism for counterclockwise direction. Lastly, it has an ambient control which includes a gas source such as argon, a flow control and exhaust system. Now, the puller microcontrolled system is used for controlling various process parameters such as temperature, crystal diameter, pull rate and rotation speeds. In crystal growing process, let us say of silicon, polycrystalline silicon is placed in the crucible and the furnace is heated above the melting temperature of silicon. For large diameters, silicon ingots, an external field is applied to the basic Czochralski puller. So, the purpose of external magnetic field is to control the concentration of defects, impurities and oxygen contents. Now students, as you can see in this figure, there is a boron trioxide cap which is essential for capping the silicon melt, and also in gallium arsenide melt it prevents the arsenic loss when the pressure on the surface is above atmospheric pressure. So in order to produce doped semiconductors, the dopant can be introduced into the melt along with the raw material. However, the limitation of the method is that the crucible material, which is usually graphite, and ambient gas can lead to the incorporation of impurities. Let us now discuss the second method, that is a float zone process. So, in order to grow semiconductor crystals with lower contaminations, the float zone process is preferred over Czochralski technique. The seed crystal is placed on a high purity polycrystalline rod at the bottom, which is held in a vertical position and is rotated. So this whole arrangement is enclosed in a quartz envelope having maintained the inert atmosphere argon. Now a small zone of the crystal is melted using a radio frequency heater which traverses the length of the rod while moving upward from the seed. Now the molten silicon is retained by the surface tension between the melting and the growing silicon faces. As the floating zone moves upwards, a single crystal silicon freezes at the zone's retreating end and grows as an extension of the seed crystal. Float zone process generally produces materials having higher resistivities as compared to Czochralski process because it can be used to purify the crystal more easily. The schematic of the float zone process is shown in this figure. Bridgman method. This method is similar to Czochralski method except that in this case the temperature in the vicinity of the seed crystal is kept below its melting point. The seed crystal is also placed in the crucible along with the polycrystalline material. However, a temperature gradient is maintained across the furnace in which crucible is placed, and the schematic of this process is shown in this figure. So, after a crystal is grown, it is separated from the seed and the ingot left is shaped and sliced into the wafers. This wafer can then be used as the preliminary material for the fabrication of semiconductor devices and integrated circuits. So students, let us now discuss the thin film growth techniques. Apart from bulk single crystals, semiconductors can also be grown in the form of thin films over a substrate. Now thin films, they provide higher surface to volume ratio and are extensively used in device and IC fabrication. There are numerous techniques to produce semiconductor thin films. However, to ensure the good quality films with minimum strain, the structure of the film and the substrate should be similar, which is also known as epitaxial growth. So the various techniques for the epitaxial growth of semiconductor thin films depends on the phase of the material to be grown, and they are described as follows. Let us first discuss the first technique, that is chemical vapor deposition. Various gases containing the material to be deposited are introduced into the reactor as shown in this figure. Upon reacting, the material is deposited in the form of a thin film on a substrate placed inside the reactor. So in a typical CVD system, the reactant gases known as precursor gases are inserted into the chamber. Upon passing through this chamber, they encounter the substrate, which is placed at some temperature, where they react and form the solid films. The gas flow and the temperature of the substrate are the two parameters that should be controlled in order to produce good quality films. So CVD has number of advantages such as flexibility of wide range of precursors, uniform thickness, conformality, etc. Moreover, it does not require ultra high vacuum, so it has certain drawbacks also in terms of safety and health hazards of the precursors. Molecular beam epitaxy (MBE). Now in this process, the source material and the substrate, they are kept in an ultra high vacuum chamber. The source material is heated and the vapors, they are taken out of a cavity such that they take the form of a molecular beam. This collimated beam is then aimed at the substrate, which is kept at some temperature. In this process, source material is placed in a crucible which is heated to an optimum temperature, thus evaporating the material and resulting in thermal energy molecular beams. So the growth conditions, they can be controlled more precisely as compared to other techniques as a consequence of control over beam flux. Moreover, due to the presence of ultra-high vacuum, various in situ analytical processes can be carried out to check and control of the process. So MBE is carried out in conditions far away from thermal equilibrium, since it is a vacuum-based process. The schematic of MBE setup is shown in this figure. Liquid phase epitaxy (LPE). Cooling of a solution containing the material to be deposited leads to the precipitation of the solute on the substrate. The system is cooled below the saturation temperature. It is similar to seeded growth bulk crystal growth techniques, but takes place at relatively lower temperatures. However, unlike MBE, it occurs under equilibrium conditions. It is a comparatively safer and cheaper technique. In addition to this, there are certain physical vapor deposition techniques to grow thin films, and these are thermal evaporation, where the material to be deposited is heated and is evaporated by resistive heating method under vacuum, resulting in a thin film at the substrate. Next is electron beam evaporation, where the heating of the target material is carried out by a focused electron beam. Lastly, we have a sputtering. Now here the target material to be deposited is bombarded by high energy ions of inert gas such as argon, which can be generated using RF or DC source. The target atoms are ejected out due to the momentum transfer and finally settled at the substrate, resulting in the formation of a thin film. PN junction. So let us now discuss the different growth techniques to fabricate a PN junction. There are various techniques to fabricate a PN junction, and they are So first we will be discussing about the grown junction. It is similar to the Chakralski method where a seed crystal melt is used to produce single crystal. However, in this method, one kind of dopant, either N-type or P-type, is introduced into the melt during the crystal growth. After some time, the other dopant is added into the melt with a concentration higher than the concentration of the initial impurity. This abrupt change in the impurity results in the formation of a p-n junction. So a single crystal consists of p and n type semiconductors. Next technique is the alloyed junction. An alloy is created between a doped semiconductor and a metal containing other type of dopant. For example, a small piece of metal containing the p-type impurity is placed on the n-type semiconductor and heated at a high temperature in inert atmosphere such that the metals melt and a part of n and p-type impurities are alloyed. The molten portion is then cooled and solidified, forming a p-n junction. Diffused junction. The p-type n-type semiconductor is heated at a high temperature in the presence of gases